If you plan to become an expert in the cyber industry, then cryptography is one of those fundamentals that you need to understand. You don't have to be a mathematician to understand how crypto algorithms work, but you do need to understand the basics, and that's why you're here. So let's start with a question. You enter your office and you have a PAN code. Now, the PAN code has 10 digits, 0 to 9, and you need to enter 4 characters passwords. Now, the question is, how many passwords are possible? Take a minute and try to answer. So the answer is 10 to the power of 4. Now, this question actually leads to some basic terminology. The key complexity is 10 digits, that is 0 to 9. The key length is 4 characters. And the key space, the amount of possibilities, is 10,000 possible values. Now, you will hear of key complexity all over this course. You will hear of key space all over this course. And you need to understand one thing. The most important thing when you deal with cryptography is the key. Anyone knows what is the algorithm, what is the cipher algorithm. But the attacker, the hacker, tries to understand what is the secret key. We see it also when it comes to passwords. Now, when it comes to passwords, the basic policy is to enter 8 characters. 8 characters out of 52 possible characters. That is A to Z, 26 characters that are uppercase, and 26 characters that are lowercase. Now, when we deal with 8 characters that are uppercase and lowercase, the amount of possibilities, the key space, is 53.5 trillion. And the entropy, a term that we will learn later on, is 45 bits. Now, when we have all the amount of symbols, digits, and characters that are available on our keyboard, and we are asked to enter 8 characters only, then the key space is 6 quadrillion, and the entropy is 52 bits. The term entropy actually means the lack of order, the lack of predictability that makes it hard for us to find out the secret key or the secret password. For that, we will see that we use randomness, we use different operations such as substitute and transpositioning the different characters or the different binary digits. So let's take a look at a Python script I wrote that will demonstrate the generation of a password and its entropy. So there it is, small script that I wrote using REPL.it. It's a Python script. Would you like to generate a random password? I'll answer yes. How many characters? Now I'll choose 9 characters. I'm not using the full base of 94 characters that are used on my keyboard. I'm using only 60 characters, that is 52 of the A to Z characters, and the digits 0 to 9 and some symbols. So the script actually generated the password itself, and it tells me that my password entropy is 54-bit, which is quite enough. So let's get back to our presentation. Now, when we speak of cryptography, we usually speak of classic cryptography, that is classic ciphers such as the Cipher Cipher and PlayFair Cipher, and the modern cryptography, that is symmetric ciphers, asymmetric ciphers, and so on. We will look at each and we will understand the fundamentals behind each. Now, when do we use cryptography or when do we use encryption? We actually use it just about anywhere. We use it when we send messages over WhatsApp, when we speak over Skype, when we connect to a secure web server over HTTPS. We use it in our Wi-Fi when we secure our Wi-Fi traffic that is using WPA2 or WPA3. We are actually using encryption. We are using it over SSL VPN and IPsec. But the most dominant usage of encryption within the last 30 years is definitely when we use our smartphones. When we use voice calls, our data is encrypted. When we store data in our smartphones, it is, at least at the last 4 to 5 years, it is encrypted. Now, why do we encrypt? We encrypt for two main reasons. The first one is confidentiality. We don't want anyone to take a look at our data and understand what is going on. The second reason is authentication. We use encryption algorithms to produce digital signatures and certificates to make sure that the other side is not a faked other side. Now, when do we encrypt? We encrypt when we store data, as in backups, and when the data is in transit, when it flows through our networks. Now let's move to some crypto terms. So the first term is the plain text. That is the original text. That is the original message. The ciphertext is the encrypted message. The encryption is the process or the function that turns the plain text to a ciphertext. Decryption, on the other side, is the reverse. It restores the plain text from the ciphertext. Now, the key is the information that is used within the encryption algorithm, that is the cipher, known only to the sender and to the receiver. The cipher is the algorithm. That is the encryption algorithms, and we will look at different encryption algorithms along this course. Cryptography is the science. It is the study of algorithms that is used for encryption. Now, let's look at an encryption. So, as we said, an encryption is actually a function that takes two inputs, a plain text and a secret key. The process is quite complicated, but the outcome is the ciphertext. That is the text that is being sent to the other side. Now, the other side also knows the encryption algorithm. It also has the same key that was used to encrypt the plain text, and the output is again the plain text. That is the process of decryption. So we can look at it also in that way. We have a plain text, we have a cipher, and we have a secret key. Those are the ingredients to produce a ciphertext. And now to another question. Can you guess what is the plain text behind that ciphertext? Okay. The plain text is actually the words welcome again. The cipher, the algorithm that I'm using is Caesar's cipher, and the secret key is 7. We will look at Caesar's cipher and understand what does it mean to use a secret key with the number 2 or 3, but that's the main idea. You have a plain text, you have a cipher, and you have a secret key. Now, there are some encryption challenges that when using encryption, we have to face. The first one is how do we generate secret keys? And the second one, which is much harder, is how do we deliver them between each side? We will look at that later on. Encryption uses many techniques, but among those techniques, the two most used are substitution. In substitution, we change one element with another. Caesar's cipher uses substitution. We will look at that. The other operation is transposition. We change the order of elements. So if we have, for example, the plain text transposition, and we change the order, we split the word transposition into columns and rows, we change the order of each letter, and we send this secret key. The secret key is the order. So the order here is 4, 3, 1, 5, and 2. Now let's look at the first position. The first position is the character T. The second position is the character R. So the ciphertext at the other side will look as if it starts with the characters N, A, T, S. But if you will place it in a matrix that has 5 columns and 3 rows and use the secret key that was sent to him, he will find the word transposition. So let's move to our first classic cipher, which is the Caesar's cipher. A Caesar's cipher is a substitute cipher. We replace one word with another. So the algorithm itself is the shifting. We shift each letter in the alphabet. The secret key is the number of times or the number of places. So if our secret key is 2, we shift the letter A and it becomes C. We shift the letter B and it becomes D. That's the secret key. So if we have, for example, a plain text that says attack at dawn and the secret key is 2, all the letters are shifted 2 places, and we have a ciphertext that starts with C, V, V, C, E, and so on. Now, if you think about it, the key space is quite limited in Caesar cipher. If we have in the English alphabet only 26 characters, we actually have 26 possible keys. And a brute force attack will be quite easy. An attacker could shift each letter 1 place, 2 places, 3 places, and finally get the plain text. But if we use the characters randomly as a secret key, then we will have a 26 factorial possible values. That is 26 possible values, double 25 double possible values, double 24 possible values. So if we have a plain text which says walking in the garden, the first letter W turns to F within the first key that is chosen randomly between the 26 possible characters. The second letter, which is A, turns out to be W. Why? Because it was randomly chosen. It wasn't chosen out of a predefined key. And there you have it. You can use a key space that is almost impossible to crack if you're using randomness. Now, Caesar cipher was used 2000 years ago. They didn't use a factorial of 26, they used only 26 possible keys. And yet it took more than 200 years to decrypt it. So let's look at a quick demonstration. Another script that is written in REPL.it. What is the message that you want to encrypt? Let's just write the word secret. What is the shift key? Let's use 3. And there we have it. That's the cipher text once it is being shifted. So now let's move to crypto cracking. How do we decrypt the message? How can we get the secret key? For that, we all usually use brute force attack. We try all possible keys. Now, when we deal with Caesar cipher and other ciphers that we will see along, there are only 26 possible keys. Nowadays, we are using binary digits. So a 128-bit key is 2. 2 is the base. It is 0 and 1. To the power of 128, a brute force will almost take forever. So at the beginning of this course, we took the pancode example. We had 0 to 9 digits, that is a base of 10 digits. We chose a 4 characters password, and the key space was 10 to the power of 4. That was 10,000 possible values. In a physical world, it is almost impossible to crack this code. In a digital world, it is a matter of seconds. Now, let's look at this table. Let's look at how long does it take to brute force attack. Now, our reference is a modern computer that is capable of 1 billion calculations in a second. Now, if we have a key space that is 2 to the power of 32, it will take him only 4 seconds. If we have a key space that is 2 to the power of 64, it will take him 584 years. But take a look what happens when we use a more modern key space that is 128-bit key or 192-bit keys. It will take him millions and billions of years. So that is actually impossible. Now, just to recap, a 2-bit key has 4 possible values. A 2 to the power of 3, that is a 3-bit key, has 8 possible values. We are speaking of a 2 to the power of 128. So let's see how a 2-bit key looks like. That is 00, 01, 10, and 11. That is the 4 possible values of a 2-bit key. If we will use a 2 to the power of 3, that is 8 possible values, we will have 000, 001, 010, 011, 100, 101, 110, and 111. That is 8 possible values. So a brute force attack on a 2 to the power of 128 key is impossible. But now let's look at the classic cipher and let's see what techniques were used to decrypt them. For that, we are using what is known as cryptanalysis. Now, cryptanalysis actually started at the 8th century, that is more than 1400 years, with the old Islam scholars. Now, they have found out that text in all forms has a very distinct fingerprint. So let's look at the English alphabet and see the frequency which characters appear in. So we can see that in the English alphabet, remember only 26 characters, the letter E appears more than 12% throughout the text. Following that, the letter T. It appears more than 9% in just about any regular text that is written. Following that, the letter A, more than 8%. So even if you have a cipher text, you can see that there are repeating characters that appears more than others. But it doesn't stop here. When you look at diagrams, you can see that S, S, E, E, L, L, F, F are more frequent. When you look at one-letter word, the word A and I are much more frequent than other one-letter words. When you look at two-letter words, of, to, in, it, they are more frequent than others. When you look at three-letter words, the and are much more frequent. And the last thing is that H appears before the letter E. That is also very frequent in our text. So we can see it in the word he, then, the. Now, knowing all that, can you try to decrypt this cipher text using the letter frequencies as we have just seen? So if we look at the cipher text, we can see that we have diagrams such as SS that appears in our text. We can also see high frequent letters such as L, 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 another L that appears quite often. And we can see two-letter word that appears here. So let's see the plain text. And the plain text is hello everyone, welcome to the event. And we can see that the letter E is used frequently in our text. We can also see TH as a diagram. We can also see WE as a diagram. And we can see the two-letter word to. So if we have frequent usage of specific letters such as E, T, A, and other letters, we can actually decrypt the ciphertext. Now let's move to another Python script that I wrote to see how frequent a specific letters appears in my text. So there we have it. Please enter your text. Let's enter, I have a secret message only for you. So let's just correct that. Now that's the secret message. Now if I'll press enter, choose a character to check its frequency. So let's choose the character E. And we can see that E appears in our message 5 times. That's the most frequent character that we are using. So how do we overcome frequency analysis? Well, there are several techniques. The first one is to delete spaces between the different words. The second technique is to use similar letters, that is S instead of Z and so on. But the best technique is just to use another algorithm that is more immune to frequency analysis. We have several algorithms like that. One of them is the Vigener cipher, and the other one is the PlayFair Cipher. The PlayFair Cipher was used in the 19th century. I actually heard about the PlayFair Cipher about 10 or 15 years ago, and when I saw the movie National Treasure, Book of Secrets, that Nicolas Cage was the leading actor. Well, in the PlayFair Cipher, we actually use diagrams, we use 5 to 5 matrix, and we use a keyword that both party knows. Now it goes like that. Let's assume that our keyword, the secret key, is Thailand. That's the word that we will use as our secret key. So on our matrix, we start with the word Thailand, and then we start the alphabet. Now, whenever there's a character that already appears in the word Thailand, we skip it. So we start with a B since we already have the letter A, C, and then we skip D since D already appears in the word Thailand. Now let's assume that we wish to encrypt the word transportation. Well, we have said that we work with diagrams. So let's start with the diagram T and R. T appears here, R appears here. So you have to look for the specific letters on your matrix. Now to encrypt the letters T and R, we will look at the same row and column that the letters appears in. So if we have the letters T and R, on the same row and column, we can see that we have the letters A and P. So T and R, that's our starting word, will become A and P on that order. So the plain text T and R becomes A and P. Now let's continue. The next diagram is A and N. Now if we look at the same row and column, we can see that we have the letters B and the letter T. So the letter B and T becomes the ciphertext, becomes the ciphertext for that diagram, for A and N, and so on. So we continue up until we encrypt the whole message. And that's how we actually encrypt messages using the PlayFair Cipher. Now, the PlayFair Cipher is a polyalphabetic cipher that is versus the Cipher Cipher, which is a monoalphabetic cipher. Now, both of them are actually using substitution in order to decrypt the message itself. It is much more hard to look for specific letter frequencies using the PlayFair Cipher, but yet you can do it using diagrams, since diagrams are also, as we have seen using Cryptanalysis, also appears frequently when we use the diagrams SS, FF, and so on. Another polyalphabetic cipher that was very popular is the Vigener cipher. In a Vigener cipher, you also need to choose a keyword that will serve as the secret key that both party knows. Now, it also works on the substitute operation technique. So if we have a plain text, hi everyone, welcome, and our key is the word Goldman, we use the word Goldman time after time just underneath the original text. Now, how do we use substitution? We look at the keyword, the first letter. We see that the first letter is G. G is number 7 in the English alphabet. So we actually shift the word, the letter H, 7 places. And so on with just about any letter. We look at its position in the alphabet and we shift the original plain text. So at the end we have a cipher text. So to conclude this part of our crypto course, a good cipher algorithm makes the letter appear random with no frequency at all. Now for this we have the perfect cipher, which is the one-time pad. The one-time pad is a polyalphabetic cipher that uses random characters according to the message text. So if we have a message that is 1000 characters, we will have a specific cipher letter for each character that is generated randomly. Now, throughout the Cold War, we have seen usage of a one-time pad, but it was only used for short messages. The key in a one-time pad is only used once. Each character is randomly chosen. There are no frequent letters and the text looks random, but it is not practical. It is not practical since you have to deliver to both sides the secret key, which is, as we have just said, the size of the plain message itself. Another reason is randomness. Randomness is a key to a good secret key. It is used in a one-time pad. There's no frequency whatsoever, but true randomness is hard to get. Where do we get randomness? In nature. When we try to generate random numbers using our computers, we actually generate a pseudo-random number since our computers are actually machines with instructions behind it. Nothing is really random. Now, up until now, we have spoken of letters, but we are not working with letters anymore. We are working with binary digit. Everything is being translated into a 1 and to a 0. So if we want to look at it that way, we have a plain binary digits, and we have a key that is generated, and our algorithm actually takes the two parts. It takes the plain bits, it takes the key, and it does some operations on it. One of them is the XOR operation, which is a binary mathematic operation. And the encrypted text is the text that is being XORed. Now, if you want to reverse and get back your plain message, you take the cipher text, you take the key, and you do the same XOR operation. Now, let's look at the terminal and see how a file is being represented. So if I look at my computer, I have many files, many text files, and let's take a text file and see just what's inside of it. So we have a text file with a message text to be encrypted. Now let's use the XXD tool and turn the text file into a binary representation, and that's how it looks. So that's how my text looks when it is converted to binary digits. We also have the secret key that is generated, and we take the two and use the XOR operation to get the encrypted text. Now if we'll use XOR calculator, let's input a message. Let's input a message that says attack at dawn. And let's use a secret key, and our key will be, let's just use ASCII. Let's just use hexadecimal digits for our key. AF F1, 2, 3, 4, 5, 6, 7, 8, and let's calculate XOR out of the two, and that's the encrypted message. Now if we will take the same message, copy it, that is encrypted message, and paste it and use the same key, the same hexadecimal key, and calculate this XOR again, we will get the same message. This concludes the first part of our cryptography course. At the second part, we will look at symmetric ciphers, we will look at asymmetric ciphers, which are much more modern ciphers, and we will see how we use our ciphers in IPsec connections, SSL VPN connections, and to ensure that the other side is the true other side using digital signatures and certificates.